So when I started this presentation, I thought, okay, this one is the last webinar on the series of the center. So I'm not gonna repeat myself talking about, let me set the pointer first. I'm not going to repeat myself talking about circular economy and the benefits of circular economy for, reaching the net zero or, the sustainability of the society. Instead, what I'm going to talk is about the fourth industrial revolution, and then how we can apply modeling, different scales of modeling, different techniques of modeling to accelerate the circular economy, how to implement a sustainable circular economy. And at the end of the webinar, I will give just 4 take-home messages, basically. So it's kind of concluding remarks and take-home messages only for them. Right. So what about the fourth industrial revolution? Everybody knows about the first industrial revolution. I started in between 1750s and the 1800s, and it was basically based on steam and water power. It was until the 1850s and 1900s where the second industrial revolution, when actually we apply what we learn on mechanization and combined with electricity to have a mass production line. Right? If you see here on the right, the global carbon emissions is with this second industrial revolution when we started producing more CO2 than the average before. Later on in the 1900s, 1950s, we had the third industrial revolution, where it's not only mass production, but also we combine with computers, and then the assembly line is non-stop, day and night, working basically moved by machines. And obviously, this non-stop production of goods and mass assembly generated a huge exponential growth of the carbon emissions on the global scale. So now we enter in the fourth industrial revolution. What it means is that we have these robots, these machines, and they are talking to themselves. They are interconnected. They are sharing information, and that's allow not only the automation as we had before, but also taking them decisions without us being present. And yeah, so that's what I summarize here. It's very important that exchange between these machines. So everybody has seen, for instance, the little robots in Amazon or Ocado warehouse, where they bring, seems chaotic, but this is an organized delivery of products from the shelves to our center devices. And why not in the future? Perhaps we will have some robots replacing further humans. Okay, so what this fourth industrial revolution requires is basically data collection, data analysis, data utilization, and exchange between different parts of an assembly chain, for instance. And what are the benefits? We have seen it previously. We've seen it also with the generation of carbon dioxide as a source of energy, right? So we saw that this industrial revolution every time speed up the process of fabrication, of manufacture of goods. And with this fourth industrial revolution, we are finding this again. We have an exponential speed of production. We have a multi-level impact of this interconnection of devices, affecting not only a vertical supply chain, but also to parallel supply chains in an horizontal way. And it's very interesting because collecting data, for instance, one of these arms taking a box, takes 100 boxes or 1,000 boxes per day. And is at the moment it takes the box, it's analyzing the size of the box, and as soon as it lifts it, it's analyzing the weight. So by just operating this robotized arm, we are getting a lot of substantial amount of information. And then one arm can pass the box to another arm, say, hey, now in the fourth industrial revolution, when we exchange of data, say, hey, careful that this box is heavy. And then we can, the second arm can say, okay, instead of taking it in a normal way, I'm going to take it in a different way. So I'm sure that, that I can carry the weight in a safe manner. So we are having decentralized decision. So someone doesn't need to be there saying, hey, this is heavy, let's take it carefully. The devices are able to make their own decisions. And this is the base of the fourth industrial revolution. So what it enables, it has also, we represent here on the right side of the slide, is a network of interconnected devices sharing information. Devices through internet or through other mechanisms exchanging information. That means that we will have a real-time interventions if something has happened. Going back to the case of the box, hey, this box is heavy, take it carefully, take it in a different manner, and better. We can have also a dynamic product improvement. So say, okay, the second arm will take the box and say, okay, this box is heavy. I'm going to take it, instead of in the traditional way, I'm going to take it in the other manner and bring it to the final destination in this other process. So we will have a dynamic improvement of service, in this case, moving a box from one side to another. And altogether is an increase in productivity, and therefore we need to adapt business models. And here is where I'm coming with the multi-scale modeling. So these are 4 different modeling techniques that we have in our center, sharing these themes. And now when the center is ongoing, we are seeing every time further exchange in information. I think this process will accelerate not only the development of our center, but also the implementation. So we're moving from business models to atomistic modeling. And now the rest of the webinar, what I'm going to do is going from these different modeling techniques and explain just very roughly what they are based and which kind of information they need. And then focusing on the circular economy of chemicals, or the production of chemicals, we will link these different methodologies to find which information they need and which information they provide. They can be interconnected and advanced in the circular economy. Right, so if we started from business models. So business model or system dynamics is a strategy of companies or different group of companies to provide some service and get some value, either economical, social, or cultural. And they are based on what I try to represent in these 3 circles. So there is a value, a good that we are providing, that it generates some revenue, either social, cultural, or economic, and is formed through a chain, a value chain. So we generate different levels of, we need different levels of information. So we need to provide what are we doing, why are we doing it, who is doing it, and how we will move it forward. So it includes information like products, the target market, we are going to provide this product, and obviously the profitability. So to have a modeling of this business model, system dynamics, we need to define a concept. Concept means we interlink from the very beginning to the very end all the different manufacturers, all the technology providers, all the users, and everything in between interconnected, with the idea of finding what's the effect of any change. For instance, we have a technological provider. So they say, okay, we have this new method. We are going to implement this method. How is going to change what it's going to do, what it's going to generate, and how it's going to change the business model. And that's the aim of this system dynamics, looking at the cause effect, recognizing it, and understanding the behavior. So, okay, yeah, system dynamics is a computer aid, so numerical simulation, and it can help us to change the strategy or even design policies. And we need to consider several points, several information that we need to provide to the system to analyze it. First, or perhaps the most important, is the concept model. So the interconnection between manufacturers, end users, technological providers, raw materials, supply chain. And that's a model. Obviously, we need the supply chain because we need to distribute and produce the product. And we will have this stock and flow diagram. And then we need to provide different scenarios. So the system dynamics, we provide a different scenario and we analyze what's the change, what's the effect of that particular change, is a particular scenario on our business model. And with that, I'm going to this example that you can find online. Well, it provides the information of the temperature that we will have in 2100. If we change, we provide different scenarios in terms of energy supply, transport, buildings, growth, carbon mobile technologies, and so on. So here, I just did something randomly. I changed the energy supply. I increased the electrification compared to nowadays. And I say we will have a small development of technology of carbon mobile. You can see how even with the decreased amount of fossil fuels, we will pass the agreement of Paris Agreement on the temperature. So I encourage you to go to this webpage and try, because it's not easy to find to be aligned with the Paris Agreement. Okay, so we need information. We need information to build our system dynamics. Now, how can we validate the model? And here is where the question, right? So we have this model here that provides us the temperature. What tells us is going to be true. So what is going to be true if the information that we provide is right. How can we estimate the information? Well, we can look at trends, we can look at the literature, we can look at previous experience. But if we improve for example, the supply chain, we will have better understanding and more accurate data. And that's, I'm going to jump to the next modeling technique, that is cross integration or supply chain. That is, it's assessing all the inputs and outputs on a process for its optimization. And it can be in a different scale, so we can go for cradle to grave, or we can have a pinch analysis, something small, so in a particular case, or just one of the factors, for instance, the temperature, the heat transfer between one process and another. And the information that we have to provide to this process integration simulation is everything that comes in and out of the process, of the supply chain. Obviously, if we want to analyze the heat transfer, in a particular case, we just need to consider everything that transfers heat, right? And if we are going to chemical reactor, so here, for instance, in a manufacturer, we are taking some products and transforming it into something else. We need to know what's the efficiency of that process. If we bring, for instance, we bring to the manufacturer product A, amount A, and then we get 50% of our final product, then we have an efficiency of 50%. And this is important, it's crucial to determine or to assess the efficiency of of this new model. So yes, we need to look at information at reaction conditions, conversion selectivities. We're talking about chemicals. Okay, now we are going to have a few examples. Here is a typical linear supply chain. And why is linear? Because we have the traditional take, make, use, and dispose. And it's for the fabrication of chemicals from oil and gas. So if we consider the inventory to define and to analyze this well-known process, we need all the inputs within the energy to extract the raw materials, to transform the raw materials, to transport the raw materials, disseminate the raw materials to the users, and then obviously environmental, in the case we are using landfill or incineration of, and all the environmental factors in between. But also we need to get the benefits. So we are selling, we are distributing a product. So we have the benefit of economical benefit. We have the benefit for society to use this product. And we should consider that. And also other sub-products like CO2. That is something that we already know we don't want. So if we change the supply chain, this supply chain, linear supply chain by a circular one, we need to include recycling, either chemical or manufacturing. We need to capture CO2, we need to recycle the CO2, and perhaps feeding it as a olefin and initial material, and then we proceed with the traditional method. Obviously, we need to feed enough of the raw material to generate the same amount of product at least. So looking at the inventory, we will need practically the same than before, that in a linear supply chain, but with additional of recycling systems. Obviously, we will decrease the amount of landfill or incineration, or hopefully avoid it, as well as the extraction of oil and gas. So here there are factors that we need to know. The previous case, the linear supply chain, is well known. It has been running for many years. We know all the in and outs of the process. Once we are establishing something new, we need to integrate a bit more. And it can be a general analysis like this one I showed before, or it can be a particular case. So here we have a manufacturer, an industry building some products. We could analyze, for instance, what's happening in certain reactors. We have the input of reactants, and we have the product. We know how the structure is, what's happening if we change the structure, what's happening if we change the flow, what's happening if we change the heat, the temperature of this process. And yeah, so the analysis of this supply chain, this cross integration, is huge benefit. So we have realistic estimates of what's going on the supply chain. We can analyze where we should modify to have a benefit, to have an increased production. Yeah, opportunities for improvement, and obviously tackle the energy requirements. Sorry. What do we know? What do we need to do? We need the inventory, as I said before. We need to feed all the information as accurate as possible, so accurate data for this inventory, and also being aware of the assumptions that we consider in our supply chain model. Let me go to a more specific case. So we have a well-known process, the synthesis of ammonia. It has been running for about 100 years, so we know how it works. We know all the ins and outs of the process, the extraction of gas, transformation of conversion of petrochemicals for methane reforming, we have the storage, the hydrogen, till we convert it with a Haber-Bosch, and we have the finally we synthesize ammonia, and we have the consumers. So we look at what do we require for this process. Obviously, we need to extract the petrol, we need to get this methane, then methane with water and some energy. We have hydrogen, we need to store the hydrogen, so it requires some energy, and then finally we need to convert the hydrogen with nitrogen from gas, from the air, to generate ammonia. Now, we know the conversions here very well because it has been really optimized for many years. We know the conversion, we know the activity, we know the conditions. For instance, the Haber-Bosch is 700 degrees at 200 atmosphere high pressure, etc. Now, obviously, we can think, okay, we need ammonia. The world is producing around 200 million tons of ammonia per year. So can we move the synthesis of ammonia to using energy sources from renewable energy sources? Okay, so we can run a process integration model and see if we can have renewable energy supplies. Well, we already know it's not. We cannot do it because the Haber-Bosch requires high temperature, constant high temperature and high pressure, while the renewable energy is oscillating, changes day and night, or winter and summer. So we know the wind is not always blowing. So we need to change. If we want to go to reach sustainability, we need to change this process. We could look at technology development. That means something that is not known, something that we are trying. We know that the electrolysis of water will give us the hydrogen that we need. And then we know we could apply mild conditions electrocatalysts to synthesize the ammonia. However, the conversion of this electrocatalyst, we know some, we don't know all of them, is not optimized. It's a process that is not optimized. We don't know the selectivity, we don't know how long this catalyst will last. And therefore, once we try to develop supply chain analysis, we need to consider some assumptions. Okay, so we could look at the literature, we could get the most efficient electrocatalyst and consider that will be the efficiency of the process, or we can take some of them and have an average, and the same for the electrolysis. So we should think, or we should look around and see if we can provide more accurate data for these processes. And that brings me to the next modeling. So this is advanced modeling. So it's numerical analysis again that can give us information about the structure of the reactor, or it can give us information of the flow of reactants or products or liquid itself within the reactor, and many more points of interest that we can bring later on. We can escalate to the supply chain and the business model. For instance, here is a flow reactor instead of a batch reactor. It's a flow reactor. We can see the change on temperature gradients. We can see the pressure. We can see the change. We could look at how the reactant changes along the reactor. And yeah, one of the most powerful points of this advanced modeling is the wide range of scales that we can analyze. So it gives information about materials, the porosity of the materials, the information of the reactor, or even can go further to a whole system. So yes, this is a very big case on the porosity. We could look at the porosity. We could look at how the reactants flow within this reactor or system with different pellets. There's a catalyst, for instance. We could see how it changes with the flow, with different regimes of flow. But I'm going to go in a bit more detail on this electrochemical cell. So electrochemical cell means that we have reactants going from one side and the products going from the other side, through one circuit. We have two sides because it's an electrochemical cell, so we have two electrodes and they are separated by a membrane. Membrane, for instance, permeable to aerosols. So the aerosols will go from one side to another and generate electricity. So this can be considered a reactor. So how can we optimize? Keep it in mind that we are always trying to optimize a model, either a business model or a supply chain or a reactor model. So here there's a list of parameters affecting the reactivity or the efficiency of this reactor, this fuel cell. So we can change the length, we can change the width, the depth of the channel. We can change the membrane thickness. We can change the temperature it runs. If this is a proton membrane, so we have the diffusion of protons through the membrane. The thickness is important. If we are generating electricity, okay, what's the concentration of chemicals, of hydrogen that we need to add? If we, for instance, we are flowing CO2 and we want to convert it to something else, CO2 and hydrogen, we want to convert to products. Which current we need to provide, so the electricity. What's the loadings of catalysts along the reactor? And many other factor parameters that I didn't list here. So then we need to optimize these parameters. One could think, okay, so we have this is the top view, for instance, our fuel cell, inlet and outlet. We will have our reactants going through this serpentine. We can divide the serpentine in different fragments and analyze the concentration of chemicals, the temperature, the gradients along the reaction flow. For instance, here we have hydrogen concentration as one of these things. We can flow hydrogen here. So at the beginning, we have high concentration of hydrogen, and as the way the hydrogen is consumed, we have a depletion of hydrogen till we reach the outlet. But yeah, so that means if we want to optimize these parameters, we need to go doing different experiments, changing a parameter every time, and look at the results. However, sometimes the parameters are interlinked, so the one depends on the other. Instead of doing all these different experiments, we could look at a digital twin, so a model with the different equations linked between them, a system of equations that define the physical model. And unless the case before where we validating the system means changing the supply chain, changing the whole model, is a substantial amount of change. Here, by just testing the physical system, we can validate our model. We can validate our system of equations. We can validate the weight of each equation. However, going backwards and forwards, even for the digital twin, might be expensive. So analyzing the concentration of every different fragment of the fuel cell is costly. It might have involved complex instruments, detailed analysis, and running to optimize all the different weights of the different parameters on all the different system equations. It might be excessive computational cost. So nowadays, although it has been running for many years, we have machine learning techniques or regression techniques. Here, explain a surrogate model. So we are building a model of a physical system that allows much faster optimization of the parameters, of the weightings, the experimental parameters to optimize and resolve the digital twin, meaning resolving the optimum parameters for the physical experimental physical reactor. So everything is explained in this slide. So we have experiments. We have our physical reactor. We have to run it with different conditions several times to start predicting, having some trends. We feed these trends into the digital or digital twin, digital space, and we set the digital twin with all the equations, all the system of equations, and start having some parameters there. Then we might run a global optimization. Global optimization means we are looking for the optimal case. We generate some experiments, new experiments, only on the digital case. So we provide an alternative experiment with different conditions. Machine learning tells us how the concentration, how the gradients of temperature, how the performance is going to be. And we go back to our initial data set. So we feed up the data set with a new value. We can run this process iteratively. So we have many alternative conditions solved by the machine learning and feeding up to the data. Obviously, it might be that the machine learning gives wrong data, wrong results, and therefore we will be contradicting our own initial results. So from time to time, we need to take these alternative experiments, run them in the physical, bring them to the physical world, run them, analyze them, and confirm if the results provided by the machine learning are correct or not. So we need to validate our system. We have methods to validate our system. In any case, that means running many cycles, many tests to validate our process. So here we have the physical results on my experiments, and here we have our surrogate model run by the machine learning. Okay, so imagine we have this electrochemical cell. We have our catalyst. Let's think on copper. It's running for a while, and we say, okay, we solve the digital model and physical model using our copper catalyst. What about if we use iron catalyst or we use silver catalyst? Then all the weightings will not work anymore. We need to start from zero. We need to start running our experiments with a new catalyst of silver, in this case, get some initial data set, feed the data set to the machine learning to learn, and the global optimization to keep providing new data. Obviously, with subsequent validation and confirmation that the data was right. So, yes, how can we save this process of iteratively test many reactors? Then that makes us jump to a lower scale. So think that the advanced modeling was working at reactor scale. It might work on different scales, but information is on the reactor that we want to provide to a supply chain. And we go several scales down to atomistic scales. Now the data that we get from these atomistic scales is slightly different. So we have energy exchange between reactants or species that we can obtain the reaction mechanism, many other bits that I will show later. But the only thing that we require is a valid theory. And when I say valid theory, is something that, for instance, comes from the first principles, so quantum mechanics. Quantum mechanics is a valid theory. It provides information on the electrons, it provides information on heats, geometries, species, and further on. DFT is well-known quantum mechanical theory. And there are many others. We could look at integrated potentials that are also valid and results are accurate. So there are many different valid theories that we just need to fit in our models and generate huge list of data. We could start, for instance, from the structure that we want to model. So here we have experimental images of high resolution TEM, and in color, there's black and white, and in color, we have our model. So the first step will be to make sure that our model agrees with the physical model, with the reality. It can be either extended material or it can be a nanoparticle. We should make sure that the information that we get agrees with the model, with the experiment. Then we could look at reactions. So here we have this animation of a graphite material where we have a defect and it's interacting with some molecules and performing some reaction. Obviously, every single step on this process is information, is energy change, is geometry optimization, is reaction steps that we should analyze. And here, that's what I bring here. So we could start with a simple mechanism of water interacting with a catalyst. So we have water interacting. So every this thick lines means an intermediate and step within this mechanism. We have the water absorbing surface, dissociates, and we get at the end hydrogen and hydroxyl groups on the surface. So we know the mechanism, we know the energies. We can extend this process to, for instance, carbon dioxide reduction. We can have different mechanisms for the conversion leading to different products. For instance, the hydrogenation of carbon dioxide might bring you to formic acid or to methanol. And analyzing the energies, we can discuss how to change certain steps. So this is one step where the selectivity for each product is controlled, and also how or which steps make the process slow. So one might think which steps to change, to modify, to have a faster conversion of carbon dioxide to methanol, for instance. So it's not only about the energy, it's about the mechanism and the selectivity and the conversion. In the same way, the information that we get from atomistic models can be translated into advanced modeling or larger experiment physical models. Here we have again the energy of a process of hydrogen evolution as a function of the concentration. So once we have a few atoms of the hydrogen atoms on the surface, they are happy together. Once we increase the concentration, they overtake zero, so it means that they are less comfortable in the surface. We are increasing the concentration, and they might evolve to the blue line here, the hydrogen gas. But before evolving, they have to pass through the red step. And this change in energy might be too large at the beginning, so they need the concentrations, the hydrogen is accumulating on the surface, the concentration is increasing till it reaches a point where it's easy to jump and evolve as an hydrogen. We can convert this information into a realistic cell. In this case, we could have a simile of a person in a bus. So you are in a bus, you're comfortable in the bus, sitting in the bus, and then the people coming to the bus, getting into the bus increases, so you are feeling less comfortable. But if you decide to get off the bus, your destination is going to be too far. So you remain on the bus, till there's a point where say, okay, I can step out, I will free myself of this huge amount of people, and just need to walk a little bit. So jumping the barrier and going to freedom. And here you can translate this information on potential. So this electrochemical cell, the potential provided by the electrochemical cell. So yeah, we see that we can bring models into experiments, and the experiments scale up to higher in level. And but yeah, so we came to this atomistic modeling with the case of changing the catalyst. What happened if we change the catalyst? So there are many theories to expand the data. For instance, we have the Bronsted-Evans Polanyi, we have the scaling factors, we have other techniques that might be combined also with machine learning. Here is just an example of data that we provide and the data that we train and the data that we get. And they are able to scale pretty well with the predicted and experimental data. And so it allows, for instance, to change from copper to silver to iron to all the different catalysts without the need of running the energy profile that I show you, the mechanism. So it's much faster and easier and with a good accuracy. So it allows us to find the optimal catalyst for this particular reaction. So now we have the optimum catalyst. We could run the model. We could run the reaction mechanism in this particular catalyst. We could run the model, and we can bring the information from the atomistic model backwards. So in a slightly higher scale, we could see how these properties of the species change, the energy of the system change with the temperature, as using the partition functions that are originated from the atomistic model. We could then approach a well-established theory, the transition state theory, to get information on microkinetics. And microkinetics allow us to define, depending the equations that we set into the microkinetics, they allow us to set batch reactors or flow reactors or many other experiments. Here, for instance, I just show the variation of a species as a function of the temperature and the time. We could see also the conversion of a particular model, and we could compare it directly with the experiments. And when I say others, I meant, for instance, experiment like temperature program distortion. So we can model, the microkinetics allows you to model experiment of temperature program distortion. So yes, so we have this thermochemistry, we have the atomistic models. All this might fit on the advanced modeling, supply chain, and business model. So if I summarize all the information that we can take, it's substantial, and not all of it will fit from the atomistic. Is required from the atomistic to the advanced, to the process integration, to the business model. Not all information is needed. So if we consider only the information that we need to pass from one model to another, to one scale to another, for instance, in an atomistic model, we could take the energy required for reactions to take place, the chemicals that we will see in the species, with the transition state theory or microkinetics, we could look at which initial reactions and initial conditions we might have to increase the efficiency of or selectivity or conversion of your reaction. Obviously, this also has limitations because it considers that it's ideally mixed, so there is no diffusion limitations, and also information on the catalyst, the resilience of the catalyst, what would happen if we have a poisoning species on the catalyst, for instance. Now we move this information upwards to the advanced technique. Obviously, the advanced modeling will have a structure of the device, of the reactor. So checking how the flow changes, if it's a flow reactor, or the size of a back reactor, or the how fast we need to agitate that reactor to limit or to avoid the limit of diffusions. All these conditions, reaction conditions, can be passed upwards to the process integration. Process integration will look at it, will fit the information of this small reactor into the whole supply chain, and look, for instance, the cost, if it's capital, the capital cost or the operational cost, if the new technology actually provides circular and green process. And if I stop, I go back to the cost. I give you an example. If we look at the ammonia synthesis that I showed you before, and looking at the atomistic model and also advanced modeling, it will tell you that ruthenium catalyst is the most efficient and the best for increasing to maximizing the conversion of hydrogen and nitrogen to form ammonia. However, if you analyze the process integration, it will tell you that ruthenium is too expensive to bring into an industry scale. then it needs to go down, change the catalyst, and look at it. So the second or third most efficient catalyst is iron. I mean, you look at the industrial scale nowadays, it's a catalyst based on iron. So iron is not the most efficient catalyst. However, it's the more the adequate, the more feasible to bring to the industrial scale. Okay. Anyway, so we take this information, we can bring it to the business model and analyze the stock and flow and the impact that this new technology will generate on the entire model. And with this, I will conclude. I want to show you just the message to take home. So the first case is that modeling, the different scale of modeling, has shown to be reliable methodology to accelerate technology and development and implementation. So not only to generate a new catalyst, but also to implement it when we combine all this modeling. If we take only the upscale, so supply chain and business model, yes, they are stand by themselves. They are able to predict cause effect or changes on the supply chain, on the business model. But they rely on assumptions and extrapolation in the same way that microkinetics, for instance, has the assumption of ideally mixed reactants. If we consider only downstream scale methods, they are self-consistent, so they are based on theories, so they generate a lot of information. However, the impact from the moment you find a new catalyst to the moment that you see the impact that this catalyst has generated on the society, it takes a long time. So this is why, as we have in our center, we combine the 4 different modeling methods or techniques that I show you now, from upscale to downscale and vice versa, to provide accurate information. And this accurate information means accurate supply chains, accurate information on the supply chain, and it means accurate information from for the business model, and means an accelerated implementation of circular economy and a fast and significant impact either from the cost or the environment or society in general. So I would like to thank you for being here today, for listening to me for a while, and that's all from me. Now I think Rana will look at the questions.
Yeah, Alberto, thanks. I did not see any question in the chat box yet.
Okay, so meanwhile we have questions, or if you have questions, I want to share. Can you see the screen now?
Yeah, we can see.
Okay, so just to let everybody know that we have the second round of the Innovate UK funding competition. So if anyone is willing to collaborate with us, please let us know. Write us an email. The contacts are available here. Thank you.